You're sitting there right now, maybe holding your phone, maybe at your desk, maybe lying in bed, and something absolutely insane is happening inside every atom of your body that you don't even know about. There's energy there, not a little bit of energy. An amount of energy so vast that if you could release it all at once, just from the atoms in your body, you'd produce an explosion that would make every nuclear weapon ever built look like a firecracker. We're talking about energy equivalent to thousands of megatons of TNT locked inside you right now. And here's the thing that's gonna blow your mind. That's not even the crazy part. The crazy part is that all around you, in what you think is empty air, in the space between your screen and your face, in the gap between the atoms in your own cells, there's even more energy. Way more energy. So much energy that physicists calculated it should tear the universe apart, but it doesn't. And we have absolutely no idea why. Oppenheimer figured this out in the 1930s and 40s. He did the math. He ran the experiments. He proved that empty space isn't empty at all. And then he built the atomic bomb and proved that the energy locked in matter could be released. And after watching Hiroshima and Nagasaki disappear in nuclear fire in August of 1945, after seeing what that knowledge could do, he spent the rest of his life haunted by a question that modern physics still can't answer. Where does all this energy come from? Why does it exist? And what does it mean that we're floating in an ocean of power we can barely comprehend, let alone control? And if you want to know what's really going on under the surface of reality, hit subscribe, because I'm just getting started. And what's coming next is going to make you question whether the universe we live in is stable, or whether we're all just incredibly lucky that it hasn't collapsed into nothingness yet. Most people think of energy as something you use. You charge your phone, energy goes in. You drive your car, energy comes out. You eat food, your body converts it to energy. Energy is a resource, a commodity, something that flows from one place to another and gets used up in the process. But that's not what energy actually is. That's not even close. Energy, at its most fundamental level, is the capacity for change. It's the potential for something to happen. And the laws of physics say that energy can never be created or destroyed, only transformed from one form to another. Which raises an obvious question. Where did all the energy in the universe come from in the first place? If energy can't be created, how did the Big Bang happen? How did the universe go from nothing to something? And the answer, the real answer that makes physicists uncomfortable, is we don't know. We genuinely don't know. We can trace the universe back to a fraction of a second after the Big Bang, to when everything was unbelievably hot and dense. But we can't go back to the moment of creation itself. The math breaks down. The theories give us infinities. And one of the people who first recognized this problem, who first understood that our theories were pointing toward something we couldn't explain, was Oppenheimer. See, Oppenheimer wasn't just the guy who built the atomic bomb. That's what history remembers. But that's like remembering Einstein only for E equals mc squared, and forgetting everything else he did. Oppenheimer was one of the most brilliant theoretical physicists of the 20th century. Before the Manhattan Project, before Los Alamos, before the war, he did groundbreaking work on quantum mechanics, on how particles behave at the smallest scales. He studied under Max Born in Germany in the late 1920s, right when quantum mechanics was being invented. He came back to America and basically created the School of Theoretical Physics in the United States. He trained a generation of physicists who would go on to make fundamental discoveries. And one of the things he worked on, one of the problems that obsessed him, was understanding what happens when you push the laws of physics to their limits. What happens inside the nucleus of an atom where the strong nuclear force is millions of times stronger than gravity? What happens when a massive star collapses and density goes to infinity. What happens in empty space at the quantum level, where particles pop in and out of existence? These weren't abstract questions for Oppenheimer. These were questions about the nature of reality itself. And the answers he found were disturbing. They revealed that the universe is far stranger, far more violent, far more precarious than anyone had imagined. And here's what he discovered about energy that still keeps physicists up at night. Energy comes in two basic forms according to Einstein's relativity. There's kinetic energy, the energy of motion, like when you throw a ball, or when the Earth orbits the Sun. And there's rest mass energy, which is the energy locked inside matter itself. That's the famous E equals mc squared equation. Every particle with mass has energy just by existing, even if it's not moving. And the amount of energy is the mass times the speed of light squared. The speed of light is about 186,000 miles per second. When you square that, you get a huge number, which means even a tiny amount of mass contains an enormous amount of energy. A single kilogram, about 2.2 pounds, if you could convert it completely to energy, would release about 25 million kilowatt-hours. That's enough to power a typical American home for over 2,000 years, from 2 pounds of matter. Any matter. Your shoe, a rock, a glass of water. The energy is there, trapped inside the atomic nuclei, held in place by the strong force. But it's there. And Oppenheimer proved this wasn't just theory. Working with other physicists in the 1930s, he helped develop the understanding of how particles and antiparticles work. See, for every type of particle, there's an antiparticle with the same mass but opposite charge. An electron has a negative charge, and its antiparticle, the positron, has a positive charge. A proton has a positive charge, and its antiparticle, the antiproton, has a negative charge. And when a particle meets its antiparticle, they annihilate. They completely destroy each other and convert all their mass into pure energy, usually in the form of gamma rays. This has been observed countless times in particle accelerators. You can create a positron, let it hit an electron, and watch them both disappear in a flash of gamma radiation. 100% mass-to-energy conversion. Perfect efficiency. And the reverse can happen too. If you have enough energy concentrated in a small enough space, you can create particle-antiparticle pairs out of nothing. Energy turning into matter. This is called pair production, and Oppenheimer did some of the early theoretical work explaining how it works. He showed that the equations of quantum mechanics predicted this. That energy and matter aren't separate things. They're two sides of the same coin, and the implications of this were staggering. It meant that the vacuum, empty space, wasn't really empty. Because if energy can spontaneously turn into particle-antiparticle pairs, and if quantum mechanics allows brief violations of energy conservation through the uncertainty principle, then empty space should be full of virtual particles popping in and out of existence. And that prediction turned out to be true. We can measure the effects of virtual particles. They change the energy levels of atoms in measurable ways. The Lamb shift, discovered in 1947, showed that virtual particles affect how electrons orbit in hydrogen atoms. The Casimir effect, measured in 1948, showed that virtual particles create a measurable force between metal plates in a vacuum. Empty space has structure. It has properties. It's not nothing. And if it's not nothing, if it has energy, then according to Einstein's general relativity, it should curve space-time. It should affect gravity. It should have an impact on how the universe expands, and this is where everything goes completely off the rails. Here's what they teach you in school about the universe. The Big Bang happened about 13.8 billion years ago. The universe has been expanding ever since. Gravity is pulling galaxies together, slowing down the expansion. Eventually, Maybe the universe will stop expanding and start collapsing back on itself in a big crunch. Or maybe it'll expand forever, getting colder and emptier until all the stars burn out and everything goes dark. That was the standard model for decades. Two possibilities: expansion slows and reverses, or expansion slows and continues forever. But here's the problem. Both those scenarios assume gravity is the only force acting on cosmic scales. And in the late 1990s, astronomers made a discovery that shattered that assumption. They were studying Type Ia supernovae, which are exploding stars that always have the same brightness. That makes them useful as distance markers. You can measure how bright they appear, compare it to how bright they actually are, and calculate how far away they are. And when astronomers measured distant supernova billions of light-years away, they found something impossible. The universe isn't slowing down, it's speeding up. The expansion is accelerating. Galaxies are flying apart from each other faster and faster. Something is pushing space apart. Some form of energy that acts opposite to gravity. They called it dark energy. And when they calculated how much dark energy there must be to explain the acceleration, they found it makes up about 68% of the total energy of the universe. More than matter. More than dark matter. More than radiation. The universe is dominated by this mysterious energy that fills all of space and pushes things apart. And nobody knows what it is. We can measure its effects. We can see how it influences the expansion rate. But we don't know where it comes from or what it's made of. And here's where Oppenheimer's work becomes relevant, because one of the leading candidates for what dark energy might be is vacuum energy. The energy of empty space. The energy from all those virtual particles popping in and out of existence. That would explain why dark energy is the same everywhere, why it fills all of space uniformly. Because if empty space itself has energy, then more space means more dark energy, which means more push to make the universe expand, which creates more space, which creates more dark energy, in a feedback loop that accelerates expansion. It fits. It makes sense. There's only one problem. When you actually calculate how much vacuum energy there should be based on quantum field theory, the answer is wrong. Catastrophically wrong. The worst prediction in the history of physics, wrong. Let me walk you through the calculation so you understand just how wrong it is. In quantum mechanics, the uncertainty principle says you can't know energy and time with perfect precision simultaneously. The relationship is delta E times delta T is greater than or equal to h bar divided by 2, where h bar is Planck's constant. What this means is that for very short times, energy can fluctuate by large amounts without violating conservation of energy. The shorter the time, the bigger the energy fluctuation that's allowed. So in any region of space, over incredibly short time intervals, particle-antiparticle pairs can pop into existence, exist for a brief moment, then annihilate. And this happens at all energy scales. Low-energy virtual particles last longer. High-energy virtual particles exist for shorter times, but they all contribute to the total energy of the vacuum. To calculate the vacuum energy density, you have to add up all possible virtual particle fluctuations at all possible energies. And here's where things get weird. There's no natural cutoff. The equations say you should add up contributions from virtual particles at arbitrarily high energies, all the way up to infinite energy, which gives you an infinite answer. Obviously, infinite energy density doesn't make sense. The universe would collapse instantly. So physicists said, okay, let's cut off the calculation at some maximum energy where we think quantum mechanics and general relativity both break down and we need a new theory. That energy scale is called the Planck energy, and it corresponds to a length scale of about 10 to the power of -35 meters. the smallest length that has physical meaning. If you do the calculation with that cutoff, you get a vacuum energy density of about 10 to the power of 94 grams per cubic centimeter. That's a 1 with 94 zeros after it. In more standard units, that's about 10 to the power of 113 joules per cubic meter. An absolutely enormous number. Now let's measure the actual vacuum energy density based on how dark energy affects the expansion of the universe. Observations of distant supernovae, of the cosmic microwave background radiation, of the large-scale structure of galaxies, all give us the same answer. The real vacuum energy density is about 10 to the power of -9 joules per cubic meter. Do you see the problem? The theory predicts 10 to the power of 113. Reality gives us 10 to the power of -9. Those two numbers differ by a factor of 10 to the power of 122. Not 10 times too big. Not a million times too big. 10 to the power of 122 times too big. To put that in perspective, the number of atoms in the observable universe is about 10 to the power of 80. We're wrong by a factor that's 10 to the power of 42 times bigger than the number of atoms in the entire universe. This is called the cosmological constant problem, and it's been called the worst theoretical prediction in the history of science. And we don't know how to fix it. Now, you're probably thinking, okay, so the theory is wrong, throw it out, and build a better theory. But here's the thing. The theory, quantum field theory, works perfectly for everything else. It's the most precisely tested scientific theory ever created. The anomalous magnetic moment of the electron, which is affected by virtual particles in exactly the way we're talking about, has been calculated using quantum field theory and measured experimentally, and they agree to better than 1 part in 10 billion. The theory works. It just gives us the wrong answer for vacuum energy, which means we're missing something fundamental, some piece of the puzzle we don't have yet, and Oppenheimer saw this coming. Not the specific numbers. He died in 1967, decades before dark energy was discovered. But he understood that there was a deep problem with vacuum energy. He worked on quantum electrodynamics in the 1930s and 40s, developing the mathematical framework for how particles and fields interact. And he kept running into infinities. Infinite energy, infinite charge, infinite probabilities. The math was trying to tell him something, but he didn't know what. Other physicists eventually figured out a technique called renormalization, which is basically a mathematical trick that lets you subtract infinity from infinity in a controlled way and get finite answers. And it works. Renormalization gives predictions that match experiments to absurd precision. But it doesn't solve the fundamental problem. It just hides it. We're sweeping the infinities under the rug instead of understanding what they mean. And Oppenheimer knew that. He knew they were papering over a crack in the foundation of physics. And he suspected that crack would eventually break open and reveal something we weren't ready for. And while you're processing that, drop a comment telling me where you're watching from. I'm always curious where in the world people are who want to understand this stuff, because what I'm about to tell you is where it gets really disturbing. The vacuum energy problem isn't just an embarrassment for theoretical physics. It's a sign that something is fundamentally wrong with our understanding of reality. And there are proposed solutions, but every single one of them is either untestable or requires us to accept something even more bizarre than the problem itself. One proposed solution is the anthropic principle. The idea is that maybe the vacuum energy can have different values in different regions of space or in different universes, and we happen to live in a region where it has the incredibly small value we observe because, if it were much larger, galaxies and stars and planets couldn't form, and we wouldn't exist to ask the question. This is not a satisfying explanation. It basically says the universe is fine-tuned for life, and the only reason the constants of nature have the values they do is because, if they didn't, we wouldn't be here to wonder about it. It's circular reasoning. It doesn't explain anything. It just gives up on finding a deeper explanation. Another proposed solution is that we're missing some symmetry in nature that cancels out most of the vacuum energy, leaving just the tiny amount we observe. This is the approach taken by supersymmetry, a theory that says every particle has a superpartner with different properties, and the contributions to vacuum energy from particles and superpartners cancel almost perfectly. But we've built the Large Hadron Collider, the most powerful particle accelerator ever created, and we haven't found any evidence for supersymmetry. No superpartners have been detected. The theory might still be true at higher energies we can't reach yet, but it's looking less and less likely. A third proposed solution is that the vacuum we're in isn't actually the lowest energy state, that there's a lower energy vacuum possible, and we're living in what's called a false vacuum, like a ball sitting in a small dip on a hillside instead of at the bottom of the valley. Stable for now, but if the right quantum fluctuation happened, the ball could roll down to the true lowest energy state. And if that happened, if the vacuum underwent a phase transition to a lower energy state, it would release an enormous amount of energy. A bubble of true vacuum would form and expand at the speed of light, destroying everything in its path, rewriting the laws of physics as it went. The entire universe would be consumed, and we'd have no warning. The bubble would arrive at the speed of light, so we'd be gone before we knew what hit us. This is called vacuum decay, and it's not science fiction. It's a real possibility that physicists take seriously. Probably won't happen. The vacuum seems stable, but we don't know for sure. We don't know if we're in a true vacuum or a false vacuum. And if it's false, we don't know how long it'll last. Could be forever. Could be tomorrow. No way to tell. Let me paint a picture of what Oppenheimer understood that most people miss. Imagine reality is like an ocean. The surface of the ocean, the part you can see, that's matter. Atoms, particles, solid things. But underneath the surface, there's vast depth. Currents, pressure, entire ecosystems moving in ways that don't affect the surface much, but are incredibly complex and powerful. And at the very bottom, in the deepest parts of the ocean, there's the ocean floor, bedrock, foundation. That's the vacuum. The quantum fields in their lowest energy state. And Oppenheimer helped us understand that the ocean floor isn't smooth. It's not uniform. It has structures, ridges, trenches, places where energy concentrates, places where new particles bubble up from the depths. The vacuum is active, it's dynamic, it's full of potential, and the amount of energy down there, in the depths, is staggering. The surface, all the matter in the universe, all the stars and galaxies, that's just foam on top of an ocean of energy so vast that we can barely measure it, let alone understand it. And here's what makes this even more mind-bending. You're not separate from the ocean. You're made of it. Every atom in your body is a disturbance in quantum fields, a wave propagating through the ocean of energy. When you die, the wave disperses. The energy doesn't go away. It just rearranges into other forms. Other waves. Other patterns. You're a temporary organization of energy that briefly thinks it's separate from the ocean it's made of. And Oppenheimer saw this. He understood it mathematically. He worked out the equations. He saw how particles and fields and forces all emerged from the same underlying quantum reality. And then he built a bomb that proved you could tap into that energy, that you could break apart atomic nuclei and release the energy Einstein's equations said was there. And it worked. July 16th, 1945, 5:29 in the morning. The Trinity test in New Mexico. The first atomic bomb. A sphere of plutonium about the size of a softball, compressed by conventional explosives until it reached critical mass, and the neutrons started flying, and the chain reaction began. And in less than a microsecond, a millionth of a second, a significant fraction of that plutonium turned into energy. Not all of it. Maybe a kilogram or so. But that was enough. The explosion was equivalent to about 22,000 tons of TNT. The fireball was brighter than the sun. The shock wave knocked people over miles away. A mushroom cloud rose 7 miles into the sky. The sand underneath the explosion melted into green glass. And Oppenheimer watched it happen. He stood there in the pre-dawn darkness and watched humanity cross a threshold we couldn't uncross. So next time you look at the night sky, remember that the darkness between the stars isn't empty. It's full of energy we can't explain. Next time you touch something solid, remember that you're not actually touching it. You're feeling electromagnetic forces between electron clouds, force fields pushing back against each other, and most of what seems solid is actually empty space, filled with quantum fluctuations. Next time someone you love smiles at you, remember that every atom in their face, every cell in their body, every thought in their brain is made of energy temporarily organized into a pattern called a person. And that pattern is impossibly unlikely and incredibly fragile and will someday disperse back into the universe it came from. And so will you. And that's not sad. That's just true. That's what Oppenheimer saw. That's what the equations told him. That's what the bomb proved. We're energy. Temporary, powerful, fragile. Beautiful because we're temporary. Meaningful because we're unlikely. Connected because we're all made of the same stuff. All waves in the same ocean. All vibrations in the same quantum fields. And the universe doesn't care whether we exist or not. But we care. We exist, and we know we exist, and we can understand how we exist, even if we can't explain why. And maybe that's enough. Maybe the mystery of why there's something rather than nothing, why the vacuum energy has the value it does, why the universe is stable enough for life. Maybe those mysteries don't need answers. Maybe they're just the backdrop for the real mystery, which is consciousness. The fact that the universe can look at itself and wonder. What would you do if you really understood what Oppenheimer understood? If you looked at matter and saw energy? If you looked at the vacuum and saw a churning ocean of potential? If you looked at existence and saw how unlikely and precious it is? Could you live the same way? Would you want to? Drop a like if this changed how you see reality. Subscribe if you want to keep discovering what physics doesn't usually tell you. And comment what Oppenheimer discovery you want me to explore next. Thanks for watching.